I wanted to check with you if for the incoming short quizzes, if you prefer to take them in the afternoon, because what's happening is that this is eating out of the lecture time and we are not catching up with the other sections. يعني إذا بنحسب every time like 20 minutes times the remaining short quizzes, this can be around 2 lectures already we have also in the past. So I don't know, or do you prefer that it be during the class time? Can you send in the chat?
I personally prefer it to be in the class time because in the afternoon بيكون في labs and classes.
Okay, so even
I
if
don't
it is
think,
in
yeah.
the late evening. Okay.
Yeah, I think you're gonna have a little bit of trouble finding a suitable time for everyone.
Okay, okay. طيب, worst case scenario, I will have to have extra sessions. I record them. You either attend them in the recording or نشوف كيف we'll catch up and we'll try to be fast. Okay, so I see.
دكتور هلا هو كله 10 minutes، فاذا بدك you can send us email يعني بركي we deal up for a specific timing باي يوم من الايام، يعني يا ام يا دبليو يا اف، يعني اقل يوم فيه ضغط او تايم كونفليكت مثلا على شي الساعه 6 كله 10 minutes، يعني 6 ل 6 10 انه ما حتفرق مع حدا، بالعكس بيكون معنا وقت
بدنا
اكثر
20 minutes basically. ايه يعني بس
اوكي، بس
تكتب له
انه
نص
بيكون معنا
ساعة
اصلا يعني تقريبا هاف ا داي ندرس زياده كمان، يعني مثلا بدل ما يكون الاربعاء الساعه
I will send a doodle. I will send a doodle for specific times, and if there is no common time that you all agree on, then we will see how to handle it. Okay, بس إنه كنت عم تخطر على بالي هاي. So okay, thank you. طيب هلا let us now we will continue finish the current mirror. And then we will look at the start of OpAmp. So last time we talked about the cascade current mirror, which is the most common type of cascade current mirror that you will typically see in the examples or in the problems that you'll see in the previous midterms. And we said that this cascade current mirror, just like the cascade amplifier, it has an effective output resistance, which is an RXY type. يعني it is basically RO is GM3 times RO3, RO2 in this example. And as we saw before, this helps us maintain the advantage, the gain advantage of a cascade amplifier. Okay, so typically it goes along with a cascade amplifier. And for this specific circuit, we have to look at what is the minimum output voltage that has to be satisfied. And what we notice in this example is that VG3, which is this node voltage, is equal to VGS4, يعني from here to here, plus VGS2, which is from here to plus, pardon me, اللي هي ذاتها يعني VGS2 or VGS1. So we rely on this property. Okay, so this VG3 is 2VT plus 2VOV. Okay, and so basically this transistor has to maintain VOV across it, and this transistor has to maintain VOV across it as well. So we will, but it has also not only VOV, it has to maintain, but to maintain VOV and to maintain VGS to be greater than VT. Okay, so if I look at two passes here, let us look at two possible passes here. في عندي constraint إنه هيدا ال VDS تكون أكبر من VOV وهي ال VDS تكون أكبر من VOV، بس في عندي constraint كمان إنه هيدا ال VGS تكون أكبر من VT. So we end up with VO equal VT plus 2VOV. هلا I'm gonna write it out for you and a clear derivation and upload it as a PDF note, just because I want to start with the operational amplifier. So هحط لكم an exact derivation for this quantity in PDF. It will be very, very clear. Okay, so but the idea is that the requirement here now becomes large, بطلت بس a single VOV, and we have a large output resistance. هلا, this is the cascade current mirror. The last type of current mirror that we are going to look at is called the Widler current source. You will see that several problems in the previous midterms, you have a current mirror where I have a certain resistance. Yani I am no longer just mirroring with a BJT. I am mirroring with the BJT with a BJT and a resistor branch. The basic idea is that the voltage from here to here is maintained the same, but the presence of this resistance allows us to deliver a different current which is smaller but relying on small resistor values. يعني أنا if I want to look at this circuit condition, and if I want to start with a circuit that delivers here a small current and I mirror it here, this will be costly for me because a small current requires a large resistor. يعني إذا أنا بدي أحط VCC for example, and then I have this BJT here on the left side, and this current هون شو هو الكرنت اللي بيقطع بهيدا الريزستور؟ شو بيكون الريفرنس كرنت إذا هيدا R and this is VBE؟ بيكون VCC minus VBE على R. So to have I reference small, I need R to be very large. Okay, so what this configuration does, it says, let me give you an easier solution. You don't have to use a very large resistor which takes a big area on the chip. You can start with a moderate I reference, but put a moderate resistor here and obtain the desired current output that you are going after. Okay, the balance for this circuit is that, yeah, we know by KCL VBE1 is equal to VBE2 plus IE2 times, if we call this IE2, so VBE1 is really by the same KVL, VBE2 plus IE2 times RE. Okay, now if we assume the approximation that I is equal to IS e to the VBE over VT, and we ignore alpha, assume beta is very large, يعني I assume IC is equal to IE, then I can really just take ln of I over IS, okay, is it times VT is equal to VB, okay. Now what I can do, I can plug those in here for each one of the two quantities, okay, and I can find a relation now for matters. So let us see how this is derived. Okay, so here they still had, if you remember, I equal IS into e to the VBE over VT minus 1. So we maintain this. Okay, but then we drop it down, and then we assume that approximately IE equals to IC, approximately that beta is very large and that we can drop the 1. Okay, so what we end up with for VBE1, it is equal to VT ln IC1 over IS, okay, which is VT ln IREF. Okay, and for this branch we have VT ln IO over IS. Okay, and if we subtract those two terms from each other, okay, then we will end up with the relation that we have here. يعني VT ln A minus VT ln B is equal to IE2 اللي هي approximately IO times RE, and therefore we end up having VT ln A over B which is approximately equal to IO over RE. فإذا نحن اعتبرنا إنه IC على IS greater than 1, we got rid of this term. اعتبرنا إنه beta very large، صار هيدي this one is approximately IO، يعني هيدي هي IO وهيدي هي IREF. Okay, and then we said this is approximately IO and we just subtracted them from each other. So we end up with this relation here. Okay, now if I want, let us say, to have IO equal to 1 milliamp and I reference equal to 1 amp, for example, then VT ln of 1 على 10 to the minus 3 is equal to 1 milliamp times RE, and I can solve for what is the desired value of RE. Okay, فإذا what we can do here in this case or in this scenario is that we start with the fact that the VBEs are equal. We plug in the equation, we assume that IC over IS is large, okay, and then we assume that IC is equal to IE because beta is large, so this becomes IO, this becomes IO, this becomes I reference, and we end up with this relation. Given IREF, given IO, I can find what is the RE that can provide me with the proper ratio between IREF and IO. Okay, anybody has any questions? So this is the basic Widler current source. Now we have finished the part 3. Okay, so we can now start looking at part 4, which is the operational amplifier. You saw the operational amplifier before in other courses. The basic thing with the operational amplifier, which we will see towards the end of the lecture, this part, is that it relies on the types of amplifiers that we have learned, and somehow it is a symmetric type of an amplifier that has 2 inputs, and so it will rely on the circuits that we studied before, but in a combined fashion. Okay, so ideal OpAmp characteristics, we are going first to study them. We are going to study the different types of operational amplifiers, and then we will see how we will build it, so that in part 5 we study the differential amplifier, the basic differential amplifier. The basic ideal amplifier has OpAmp. It has 2 pins. منه the regular amplifier. I am not studying. Before we studied in the course the symbol of the regular amplifier, which has 1 pin, 1 reference, maybe voltage or 2, and 1 output pin. This one, it has 2 ports. Okay, 1 that is negative and 1 that is positive, so 1 and 2. It can have 2 supplies, plus VCC and minus VEE, and it has its output voltage. So clearly it's going to receive 2 inputs. I can set one of them to ground and the other to a regular signal, but it has 2 inputs from a small signal perspective. Now, this amplifier is characterized by what we call the open loop gain. So this is a very important term. This open loop gain A, it relates the output to the 2 voltages V1 and V2, which are applied at the negative terminal and the positive terminal. And specifically, the relation is that VO is equal to A into V2 minus V1. Okay, so the difference between the 2 is satisfied, multiplied by A gives me the output. Why do we call this the open loop gain? Because later, once we add more components that provide me some feedback from the output to the input, if I solve for VO over Vn, which is in this case VO over V1 if Vn is applied here, for example, then this will be different because the placement of the resistance will give me what we call the closed loop gain. Okay, and with feedback, I will have a gain that will be function of A and the resistors, as we will see next. Okay? Okay, so let us differentiate between the open loop gain and the other formats. So this input here, V2, is called the non-inverting input, and this is basically because the gain, open loop gain, is multiplied by it, whereas this pin is the inverting input, and this is A into V2 minus V1. So we have here minus V1. So this is why this is an inverting terminal, and we refer to this as the inverting input. هلا, in the circuit interpretation, we will explain why it is inverting. So V3 equal A into V2 minus V1. This is called the open loop gain. And this circuit is characterized by infinite input impedance. ما عنده input impedance لأن الcurrent zero at both terminals. The ideal one, of course. Zero output impedance. ما عنده RO. It is zero. Okay. And it has infinite open loop gain. So if it is ideal, it has infinite open loop gain. Okay. So if this gain is infinite, and if this is finite, okay, then, sorry, and if the output, pardon me, if this is infinite, and if I can sense an output that is finite, then under this scenario, this has to be zero. Okay, لأن ما فيني طلع finite من infinite and a finite value. Okay, so under the case of infinite open loop gain, and if A tends to infinity, we have a condition that V2 is equal to V1. The two nodes become equal. Okay, and we will see how we will use this. Now, we sometimes will not will tell you this is not ideal, but it has still infinite, or it has infinite impedance, zero output, but A is finite. Okay, so we can have different combinations of non-ideal, but for the ideal case, A is infinity, there is no input impedance, no output resistance, zero output impedance, and under this condition of A infinite, V2 has to be equal to V1. Okay, anybody has any questions? هلا, typically, ideally, if VCC and VEE are 15 and minus 15 volts, in real life, if you get a discrete op-amp, the output of the op-amp cannot reach all the way to VCC. And this can be explained, for example, if I have a current mirror, okay, where part of it I have here the amplifier, and this is VCC. يعني هيدا هو كله الأوب أمب. بس let us say في عنا current mirror. في عندي I have a voltage drop here before I start supplying the amplifier. So VO, if you recollect, has constraints from the circuit itself to be in saturation and from the current mirrors to be in saturation, and therefore its VO cannot be full rail. ما فيها توصل للfull VDD. There are some exceptions where the drop is a few millivolt, هذه هيك general knowledge for us. But what really matters to us is that if A tends to infinity and VO between its saturating limits, يعني it is finite, then V2 and V1 have to become equal as we just discussed. Okay? طيب, great. So هلا لقينا there are many configurations. This is the most popular configuration where I am supplying an input voltage. Okay, so this is the circuitry that is connected external to the amplifier. I have the amplifier. I put R2 between 1 and output, and I put R1 between Vin and 1, and I grounded node 2. So now my amplifier has some feedback. Okay, and this feedback or this configuration, the input is connected to the negative terminal. So this is going to be an inverting amplifier. So let us see what is the relation between VO and Vn. Now, the first thing that I will say, if this is ideal, this means that V2 equals V1. This means that this node is also ground or zero, right? The second thing that I am going to think of is that this amplifier is ideal, so the current that is going into it is zero here. And therefore now, the current that is going to flow in this branch is going to be split into I equals 0 and into the current that is flowing into R2. Okay, so if I want to find the relation between VO and Vn, all I have to do is really to solve KCL at this node. So the current I1 and the current I2, I will have I1 is equal to 0 plus I2. I1 is Vn minus V1 over R1, and I2 is equal to V1 minus VO over R2. But V1 is 0 by virtue that V2 is 0. So this tells me that Vn over R1 is equal to minus VO over R2, and therefore VO is equal to minus R2 over R1 times Vn. So this is the gain of the circuit. Now I have the open loop gain, okay, A tending to infinity, but the circuit with the feedback gave me a gain of minus R2 over R1. Okay, so VO over Vn is equal to minus R2 over R1. Okay, anybody has any questions? طيب, great. So let us see what the slide is telling us here. So, okay, so this is the derivation. Now for this circuit up here, what we have is that, what is the input resistance? This is IN, always whatever is the river. So IN, so VN, okay. What is the relation of IN and VN? What is the input resistance of this circuit? And the ground على node 1. I have a ground at node 1. So what do I know about Vn? Vn is equal to In times R1. يعني Rn is equal to Vn على In, and it is equal to R1. So the input resistance is R1. The output resistance for the amplifier, what do we do with Vn? We set it equal to what? 0, right? So we set Vn for the output resistance to be equal to 0. Okay, and therefore the current that is flowing in here is 0. The current that is flowing in here is 0. Okay, and therefore the effective resistance current that is flowing in here, we end, okay, I'm not going to confuse you with this. We end up with RO that is equal to 0. Okay, so we end up with output resistance that is equal to 0, and this happens when I do Vx. Okay, and I have Ix here, and Vx over Ix will end up giving me an output resistance that is equal to 0. I will write the derivation for you about this on a note. So I will write 2 derivations for you. Hello. What we have here is that, let us look now, what happens now. So this derivation was when we said that the gain is tending to infinity. Okay, so this derivation is when we said that the gain is tending to infinity. Now, let us see what happens when we say that the gain is finite. When we say that the gain is finite, so the gain is finite, okay? ساعتها what will happen? I can no longer say that this is a ground, but I still have the current that is flowing here equal to 0. So therefore, I will have Vn minus V1 over R1, right, is equal to V1 minus VO over R2. But V1 is not 0. What is V1? I have a relation that says VO is equal to A into V2 minus V1. V2 is for sure 0. Okay, so this is 0, and this is equal minus A times V1. Okay, so this is equal to minus A times V1. Okay, and now I can then find the relation, therefore V1 is equal to minus VO over A. So I'm going to take this relation here, okay, and I'm going to plug it here and plug it here, and I will end up with an equation that is function of Vn and Vo, and I will end up with a complex expression for VO over Vn. If we examine this expression of VO over Vn, it is function of minus R2 over R1 over an expression that has the gain A. So this expression when A tends to infinity هو كلهم حيروحوا حيصيروا 0. It is going to tend to minus R2 over R1. So this is the general expression which is function of A, and this general expression which is function of A, we can test it when A tends to infinity and it will give us what we obtained in the previous slide. Okay, so لكينا when A is finite, we are still assuming that the current that is flowing here is 0. Okay, so anybody has any questions؟ يعني قلنا هيدا الكرنت بيساوي هيدا الكرنت. Okay, طيب let us now see what this amplifier is. So this amplifier here, now instead of connecting one signal to this node, it connected many signals. Okay, it is ideal, so this node voltage here is 0 and the current that is flowing here is 0. So by means of KCL, this current is the same as this current, and this current is nothing but the sum of many individual currents, right? So what this tells me is that V1 over V1 minus 0 over R1, right? Plus V2 minus 0 over R2 plus Vn minus 0 over Rn, اللي هو هيدا الكرنت, is equal to 0 minus VO over R feedback. Okay, so now all of a sudden I can find the relation between VO and all of these inputs, and this relation is a weighted sum. يعني VO becomes equal minus summation of RF over RI times VI. Okay, so this allows me to have an operational amplifier that is performing a weighted sum of all the input signals. Okay, anybody has any questions? Okay, so now we looked at the inverting application. We have now the non-inverting. The non-inverting, the input is going to be connected to the positive terminal of the amplifier, but I still have feedback resistors that are placed between the output and the inverting terminal, and then a resistor between the inverting terminal and the ground. If A is infinite, by this virtue, this value here will be Vn, okay, and this is ideal, so I will still have a current here that is equal to 0 flowing into this input terminal, and therefore all the current that is coming here is really continuing in the resistor R2. So accordingly, what we will have is that 0 minus Vi over R1 is equal to Vi minus Vo over R2. Okay, now I have a relation between R1 and R2. I can find the closed loop gain. Okay, and so if we apply this, we will end up with the relation that says Vo is equal to Vn into 1 plus R2 over R1. Okay, into 1 plus R2 over R1. Great. So this means that I can design R2 over R1 if it is greater than 1, I will have a gain, and the gain for VO over Vn is positive. So this is non-inverting amplifier configuration. يعني VO is in phase with Vn. Okay? Anybody has any questions? Accordingly, now if we have this relation for the finite A, all we have to say is, well, these two nodes are not the same, but I know that VO is equal to A into V2 minus V1. Okay, so I have a relation that says VO is equal to A into Vn minus V1, and I need to find V1 as function of Vn and Vo, okay, and then plug it in by writing the relation here. If this is V1, 0 minus V1 over R1 is equal V1 minus VO over R2, and I have the relation of VO and Vn here and V1. I replace this value and I find that this is the gain AV, okay, of the amplifier as function of R2 R1 and A. انتبهوا إنه هاي هي AV لأن هي VO على VN بالpresence of the feedback. A هي ال open loop gain. هيدي بس انتبهوا لهاي. When A tend to infinity بيصير عندي الgain AV VO على VN in the closed feedback implementation, and the feedback implementation equal to 1 plus R2R. Okay? So this is the relation that we have here. Okay? طيب great. هلا أنا I'm going to stop here.